Okay, so this lecture will be about solving PDEs by the method of separation of variables. Okay, so in Math 256, there are really just three PDEs that are of interest. There's the simplified heat or diffusion equation, there's the wave equation, and Laplace's equation. So for the first one, we have a single time derivative, so we usually provide an initial condition. That could be, for example, the distribution of temperature along a rod at time t is equal to 0, and there are two space derivatives, so we also supply two boundary conditions. So for example, if the ends of the rod are held at a certain temperature, I could impose something like u at 0 and u at pi, if that was the length of the rod, as 0. Okay, so that's one model type of problem. Right? We supply the PDE, an initial condition and boundary conditions. The wave equation has two time derivatives, so we need a second initial condition. The third equation, Laplace's equation, I've got different independent variables, x and y. Here we're searching for something which depends on two space variables rather than space and time. And you'd need boundary conditions in both x and y, two of them. Right, so that's the setting. So to kick off, I'm going to solve that problem. And the way we do it is by breaking it down and solving a couple of ODEs, rather than attacking it as a PDE. So let's get going. Separating the variables, what do we mean by that? Well, we have a u and an x and a t. I'll replace that by a function of x and a function of t. And they're split, they're separated, hence the name of the method. Now, if I compute derivatives, so my shorthand notation for derivatives is subscripts, as written in the PDEs. So when I do an x derivative, I just differentiate the big X, and that's the only thing that depends upon big X, so I can just use a prime to denote the derivative with respect to the argument. And there's a ut, that would be differentiating the big T, so I could write it as x times big T. And then in the PDE over there, I just need the second x derivative, so we end up with x prime prime times t. Right, so that's separating the variables. I can feed these into the PDE, and I will get x t prime, that's du dt, is equal to x prime prime t, that's u xx. The trick now is to manipulate this. I'm going to divide by the big T, and then I divide by the x. So what I get left with at this point is t primed over t is x prime primed over x, which one might regard as not having made much progress. However, once I've written it this way, I realize that I have a function on one side, which only depends upon t. This is a function of t. On the other side, I have only a function of x. T and x are independent variables. That means, for example, I could be thinking about this as a heat diffusion problem along a rod, for example. I could have let the temperature diffuse, and then I decide to observe what the temperature looks like at a given time. So I freeze time. I say t is some constant. That means that's a constant at that moment of time. So it means that this function of x has to be constant. Alternatively, I could turn it around a little bit and say, all right, I'm going to stand at a particular position along the rod, so I'm going to freeze x, and then I can look at what happens in time. That tells me that this is a constant, because I've frozen x, so this function of time has to be a constant. So it's actually quite a powerful rewrite of the PDE, because it means that t primed over t has to be a constant, and x prime primed over x has to be the same constant. But if that's a constant, and that's the same constant, then I've just got a couple of ODEs. I just need to come up with a symbol to represent that constant. I'm going to use minus lambda here and there. So my ODEs are x prime primed plus lambda x is equal to 0, and t primed plus lambda t is equal to 0. So I advertised in a previous lecture that when we deal with PDEs and we exploit separation of variables, we end up solving ODEs. There they are. This one's second order, this one's first order. The order of the differential equations is related to the order of the derivatives in the original PDE. Second order in space, we got an x prime primed. First order in time, we get a t prime. It's constant coefficient. So we can effortlessly solve both ODEs using the technology that we developed earlier on in the course. This one, for example, tells us immediately that big T is some constant, let's call it c, times e to the minus lambda t. This one has an auxiliary equation, which is m squared plus lambda is 0. That's if we pose x as a constant times e to the mx. Right, so I get complex solutions for m, like they're purely imaginary, and so we end up with x being either a constant, let's call it big A, times the cosine of the square root of lambda x, or another constant, sine of root lambda x. Okay, that's basically solving the problem. Right, we've dealt with the PDE, or equivalently the two ODEs that we get by separating variables. I should just say one thing, which is that lambda here has a special importance in the methodology, and it's usually referred to as the separation constant. Okay. Right, at this point, we are now ready to move on and think about the rest of the problem. The rest of the problem is the combination of the boundary conditions and the initial condition. The initial condition, it says that there's some distribution of u at t is equal to 0, and I haven't actually said what it is. It's some function f of x. That looks hard, so let's leave that for later. These conditions, on the other hand, are much easier to deal with, and given our form for the solution, that's going to immediately tell us something about these solutions for big X. As I say, this one's a bit more complicated, so we reserve dealing with that until the end. Right, so let's summarize what we've accomplished so far. We've taken our PDE. Let's get rid of these for the moment. We've taken the PDE. We separated variables. The separation introduced two new functions, the big X and the big T, and a separation constant. The PDE then was cleverly rewritten so that we had a function of X is equal to a function of T, and because they're different variables and independent of one another. That means they both have to equal the separation constant. This leads us to the ODEs that we solve. Right? And then we're going to pick on the simple conditions, the simple extra conditions, which in this case are those two boundary conditions, and they're going to help us deal with the choices of the solution for big X, and then finally we're going to have to deal with that. Right? So that's the general way these PDE problems will work out in Math 256. Okay, so we've got U at 0 and t is equal to 0. So that says that x of 0 times t of t is equal to 0. Well, I don't want big T to vanish, because otherwise I won't get anything. So I need the big X function to vanish at x is equal to 0. And similarly, when I put pi, I also need to get 0. Right, so those boundary conditions on U translate to boundary conditions on big X. And my solution down there, I could say, okay, well, I can easily write a combo of them. So I would be tempted to write a slightly more general solution, like so. But putting 0 in here would tell me that A has to vanish. Right, sine of 0 is 0, cosine of 0 is 1. Now, having put A to 0, I can now impose the other condition. So I get 0 is equal to B times sine of the square root of lambda times pi. It's obviously not a very good thing to put B is equal to 0, because then I don't get anything but a trivial solution for x. So I really need the sine function to vanish to get anywhere here. And that's quite handy, because I've introduced the separation constant in order to reconcile the fact that I've got a function of t as a function of x over there, but I don't know what it is. This tells me what it is. I know that the sine of pi times an integer is 0. So in other words, the square root of lambda has to be an integer. Let's call it n. So that's 1, 2, and so on. So lambda is n squared. That's what I learn from that boundary condition. This boundary condition tells me that I've just got the sine function. Okay, so at this point, I've now dealt with the PDE, I've dealt with those boundary conditions. I can write out what U is. So let me go back here and do that. Okay. So, U is equal to a constant b, sine, and the square root of lambda is n. And then t is c, e to the minus lambda, that's n squared. Okay, I don't really need an arbitrary constant there and an arbitrary constant here. That's just really one single arbitrary constant. So let's call that little b sine nx e to the minus n squared t. That's my solution. But I should also bear in mind that n is any integer. So there's actually a lot of solutions there, an infinite number, in fact. Okay. Great. We've now solved the problem by separation of variables, and we've got the solutions. There's still this small matter, or perhaps it's a big matter, of dealing with that condition. Let me get some space here. Maybe I'll use this. Okay. Great. So I've got my solution, and the last thing to do is to make sure I can then satisfy the final condition. Okay. Well, I have to put t is equal to 0. So u of x and 0 is f of x from here. But from here, it's b sine nx. Okay, well, at this point, there's really two possibilities. One possibility is you come along and say to your initial condition, are you lucky, initial condition? What do I mean by that? Well, let's say that f of x is equal to 10, some number, sine 33x. If we're in this incredibly lucky situation that f happens to be one of the sine functions, I can just compare them and conclude that b needs to be 10 and n is 33. At which point I record the fact that u of x and t is equal to 10, that's the value of b, e to the minus n squared, that's minus whatever 33 squared is, times t, times sine 33x. That's the answer. Now, when we first met PDEs in a previous lecture, I made up a solution of the heat equation, and it was something like this. And this is obviously a way one can deduce certain specific solutions of the heat equation. Right? I solve the problem with separation of variables, I get these types of solutions, and so if my initial condition takes that form, I'm done. However, life is not that simple. What we're actually more interested in is solving this problem for any old f. If we have any old f, it's not going to be one of the sine functions, and clearly we've got to do a lot more. So what can we do? So back to the drawing board. We have a function f which is not one of the sine functions. What can we do? Well, to deal with something that's a bit more general, it's helpful if we can be as general as possible there. So, second option is more generally. And this is for a non-specific f, not one of the sine functions. So it's a more general f. Okay. So, I want to be more general, so I want to be as general as possible there. Well, I've got all of these n's to play with. I don't want to just necessarily choose one of them. And moreover, when I mess around here, I don't necessarily want to use the same constant in front of each of these different solutions for different values of n. It's a linear problem. I can just take a general superposition of all of these to come up with a more general solution. So the PDE is linear. A general solution is, so I take my u, and I'm just going to sum over all possible values of n. I'll get a bit more space here. So I've got a sum over n. So n's going to go from 1 to infinity. I've got a b, which might be different for each of these. So let's put all of the different constants as b sub n to allow for that. Then I've got sine nx e to the minus n squared t. Right? That's my general solution. Okay, So the final part of the problem now is to then try and get the series, the full series, the most general form of the solution that I can come up with. I need to get that to agree with the initial condition. So here we go. I put t is equal to 0. I need to align what I get with f of x. So I need those two to be the same. This is an infinite series with some unknown coefficients. I've got to pick those coefficients to satisfy that. So that's the final part of the problem. Now, right before we started talking about PDEs, we talked about Fourier series. And looking at this, you start to realize that this is part of a Fourier series. Let me just remind you about the Fourier series. Okay. Bit of space. Right, so we're no longer lucky. We're dealing with a more general situation where we have whatever f there. It's got to be shoved in there, and I've got to pick the b coefficients to get it to work. So that's the objective of what we're going to do next. So how can we proceed? I've mentioned Fourier series. So let's remind ourselves about Fourier series. It wasn't that long ago, fortunately. So if I have a periodic function, I have the following information. What color should I use? Let's go with lurid pink. Okay, 2 pi periodic f of x. If I have this 2 pi periodic function, then its Fourier series is this. That's the full Fourier series. And we talked about that, and the old goal was to be given an f and then figure out what the coefficients were. And the coefficients, the a0, an, and the bn, I could get them by doing an integral. So I integrated from minus pi to pi, divided by pi. I took my function, f, and then to get one of these three coefficients, I multiply by either 1, cosine nx, or sine nx. Right, so that's the formula for the coefficients of the Fourier series. Okay. So at this point, we sort of see what we need, because what we need is a certain part of this series. I want, in fact, the series without the a0 and the an. But if the f here is odd, one of the implications that we talked about and established was that all of the a's were 0. And the b, I could just get it from here, or I could also just get it from integrating from 0 to pi, dividing by pi, and multiplying by 2. That's the Fourier series for an odd 2 pi periodic function. That was the technology from Fourier series theory. Okay. There's still a bit of a discrepancy between the left and the right. Let's just go back and look. We have the PDE. We're solving that over a certain interval, and given where the boundaries were. we're solving it between x is 0 and x is pi. And we're saying that it has to vanish at the ends. Right, so u or f, right, what we're interested in is defining them between 0 and pi and then making sure that they vanish at the ends. The Fourier series theory, that just applies when I have a function that's 2 pi periodic. And if it happens also to be odd, then I know that I don't have the cosine and the constant in the Fourier series. So this is something where I'm thinking about periodic functions, but they're odd. Over here, I don't have any statement about periodicity. I've got this statement that I've got something that's defined only between 0 and pi, and it should vanish at the ends. It seems as though I've got two separate problems here. So how do we proceed? Well, the fact that we've only solved this problem between 0 and pi, and we've got no information outside that interval, allows us to be clever about that. Okay, so if we're not saying anything about what happens below 0 or above pi, then we can demand something about what happens there in order to connect this problem with that problem. Now maybe at this stage you are starting to have a feeling that we're going to play that game again, where we talked about extending functions. Right? So here I've got my problem that's defined between 0 and pi. Right? This is where my PDE lives, and there's no information provided outside that. This is an odd 2 pi periodic function, so how can I get these two things to be the same? Well, the first thing I'm going to do is I'm going to come along and I'm going to say, okay, let's extend the functions here, the f and the u. I'm going to extend them first to here, to minus pi to 0. I'll make that extension first, and I'll demand that it's odd. Right? So that's the first step. I'm going to take the odd extension, at which point I've got an odd function defined between minus pi and pi, and then I make it periodic, and I make the 2 pi periodic extension. Right? In other words, I take my functions here, which only live on that interval, I make them odd and 2 pi periodic, at which point these functions are equivalent to the functions there. And the fact that I insisted that it was odd here means that I have a Fourier series for it that only depends on the sine functions. The a0 and the an's are all 0. So at that point, I say, oh, well, I've extended the problem here in such a way that it can be related completely to this Fourier series problem, and I know how to pick the bn's. That's the formula for the bn. So at this point, I've now solved the problem. The Fourier series theory tells me that I'm justified in representing f of x as a bunch of sines, and it gives me the formula for the bn. Okay, so let me summarize all of that in more detail. Let's keep the 2 pi periodic function there, but I'm going to dispense with this. Okay, I got my PDE problem stated there, so let's keep that, and the solutions there. But maybe I don't need this bit. And there's this stuff about extensions at the bottom. I'll summarize that as well. Okay. Quick cleanup. Right, the problem that we start with is here. Then we separate variables. So step one is to separate variables. Right, u I replace by big X of x, big T of t. I take the PDE and I write it as a function of x, as a function of t, which therefore has to be my separation constant. This seems to be running out of it. Right, that means that I've got two ODEs to solve. I solve for x and t. I apply the BCs, the boundary conditions, and it tells me at that point what lambda is. It was n squared, where n was an integer. Right? I then formulate the general solution. There it is. And then finally, I apply the initial condition. That means I've got to pick the coefficients of the general solution to satisfy that. In order to do that, I extend f, equivalently u, as an odd 2 pi periodic function. And that implies that b n should be 2 over pi, the integral from 0 to pi of f of x sine nx. Right, so that's the strategy for solving the PDE. Now, as you might imagine, the only calculational detail that still needs to be done once you've gone through and solved the ODEs for the big X and the big T and applied the boundary conditions, the only thing that you might still need to do is to take whatever f you've been given, put it in there, and do the integral. i.e., the last algebraic detail is to compute the coefficient of the Fourier series, which is what I told you the exercise was when you were dealing with Fourier series like that. It was always about calculating those integrals. And it's about calculating the integral down there in this particular case. Anyway, at this stage, we can declare victory. We can say, hey, I put in my f there, calculate the coefficients, those numbers appear there and there. This is the one that you really care about because that's the solution of the PDE. And we're done. Okay. So that's an example where we've taken the heat equation with these boundary conditions and that initial condition, and we've applied separation of variables. Let's try a different example, just to see the method in action on something slightly different. So I'm going to switch the heat equation for one of the other three important PDEs. Let's go with Laplace's equation. So I'll solve Laplace's equation, and then there's going to be some boundary conditions to replace this combo of boundary and initial conditions. But we're going to go through the same exercise. Right? There's going to be a separation of variables step, a reduction to a couple of ODEs, solving those ODEs, applying some of the boundary conditions, formulating a general solution, and then finally applying the slightly more complicated extra condition, right? This was the slightly more complicated extra condition that we reserved to the end. We're going to meet something similar for Laplace's equation. So for Laplace's equation, we'll do the same thing. We'll split the boundary conditions up into two parts, simple and complicated. We apply the simple ones first, the more complicated one at the end. And at some stage, we're going to be needing something from the Fourier series theory. Okay, so without more ado, let's get going. All right, so I want to keep that. I just want to change the problem here. Let's get rid of the header. Okay. So, Laplace's equation, that's something that comes up when you're looking at field problems, field-type problems, electrostatic or gravitational or something like that. In 2D, I'm looking for this equation, right? This is the Laplacian of u is equal to 0 for u as a function of x and y. That's the problem, if you like del squared or Laplacian. This is really the PDE. All right, now I want to solve this, and I'm going to solve this on the domain. Here's x and here is y. I'm going to solve it in the upper half of the plane. Okay? And I'm going to solve it subject to some conditions. Right? So I'm solving it above the x-axis. Okay? That means I'm going to have some condition at y is equal to 0. That's going to equal something. Let's call it f of x. And then I'm also going to demand that as I go off to infinity, as y goes to infinity, I'm going to say that things decay. Things go to 0 as I go through the roof. And in particular, I'm going to say that the y derivative of u goes to 0 as I go through the roof. And then let's take a strip of this plane. So I'm going to go from x is equal to 0 to x is equal to L. And I'm going to apply boundary conditions there and there. Let me put ux of 0 and y is equal to 0, and ux of Ly is equal to 0. Right, so I've got a derivative condition there. I've got a derivative condition there. There's something more complicated that I'm applying down here. And then things decay as I go up. Or du dy goes to 0. So that's the statement of the problem. So let's look at it a second. So before we jump in, let's imagine what we need to do. So the first step will be to separate variables there. Fine. We're going to put in u of x and y, following the strategy of my symbology. I'll call it big X of x and big Y of y. Right, I'm going to take that, shove it in there, and reorganize it so I need a function of x as a function of y. Right, the only difference is that I've got y's instead of t's in this problem compared to the previous one. Okay, so that's sort of the first step. I get ODEs. And I'm aiming to solve them. And I need to use some of these conditions to help solve that problem. So the strategy last time was to look at the additional bits of information. That was the boundary and initial conditions. Now it's just these boundary conditions. and split them up and say, well, there's some more complicated ones. That's clearly the boundary conditions in y here, because I've got this unknown function that I need to put in there. And then some simple ones in x. So I'm going to do the split again. I'm going to use the simple ones early on and the more complicated ones at the end. All right? So I'll use the BCs in x first to simplify the solutions for x and y. And in fact, if I think back at the problem with the heat equation, it also told me what the separation constant was, and that's going to have to be true here as well. So I also find lambda, whatever my separation constant is, however it sort of comes into these problems, I'm going to need to find it by applying those conditions. Right? These are the simple ones. Having done that, I may say, aha, now hopefully I'm going to get lots of solutions here, so I can formulate a general solution. And with that general solution, hopefully it's going to involve something that looks like a Fourier series. I'm then going to come along and use it to make sure I can satisfy those. Right? It's somewhat similar to the diffusion equation case, right? We use the boundary conditions in x immediately after solving the ODEs, and then the complicated initial condition in time, that's now boundary conditions in y, we save those to last in a general solution, and that's where a Fourier series type thing will come in. Right, so that's looking ahead. Right, so at this point we may as well get going. First step is here. Right, that's step one. I put my decomposition into there. So that means I've got two derivatives on big X times y for uxx, and then I've got x times two derivatives on y for the other one. I need to write this like that. So I can do that by dividing by big X and then dividing by big Y. So I get big X prime prime divided by big X for the first term, and then that's the function of X. Then the other one becomes big Y prime prime divided by Y. Let's shove that on the other side of the equation. There's my function of X. There's my function of Y. That can only be true because X and Y are independent coordinates. If these things, I forgot a minus sign there. If these things equal a separation constant, right? So the Y prime prime divided by the Y goes over the other side to give me the minus sign. I've got X prime primed over X is the separation constant. Let me just recall the previous example. That was X prime primed over X was equal to T primed over T, and I said, oh, hey, let's make that equal to minus lambda. Great. Well, I've got X prime primed over X again. Let's do the same thing. Just following the same strategy. Great. That was this part. I've got my ODEs. I've got X prime primed plus lambda X is equal to 0, and I've got Y prime primed minus lambda Y is equal to 0. That's what I get from there. Okay. Job done there. Now I have to solve them and then use the boundary conditions, these boundary conditions. Okay, so let's do that. So let's take the X equation and solve it. In fact, it's the same as the one we had before. So I can write X as some A cosine of root lambda X plus B sine of root lambda X. That's exactly what I wrote down before. And I need to make sure I can satisfy these. All right, so Ux at 0 for all y's, that's got to vanish. So that translates to saying that the derivative of this, right, x primed of 0 has to vanish. And then the other one, which is the derivative at L, and I've got the boundary now at L rather than pi, that's going to tell us that x primed of L needs to vanish. Okay, so I've got my solutions here. I can feed them into there. The first condition is going to get rid of one of these, right? Because if I differentiate this, this turns into a sine function. Sine of 0 is 0, so it doesn't appear. This derivative here, that turns into a cosine. Cosine of 0 is 1. So this one is going to basically tell us something about b. The other one, when I apply that, hopefully that will tell us something about lambda. Let's do it. Okay. So I've applied this. And I've solved the ODEs. Right, so this is step 2 here. This is what we're doing down here. Okay. Right, so we've dealt with the stuff down here. I can get rid of that. Splendid. Okay, this is step 3. I'm not there yet. All right, I'm on step 2. Still going through that. All right, so let's have a look. So x primed is equal to minus a, the square root of lambda, sine the square root of lambda, x plus b, square root of lambda, cosine of the square root of lambda x. And that's doing the derivative. Now I put x is equal to 0 for the first boundary condition, and it tells us that 0 needs to be b times the square root of lambda. Now I put L. I need 0 to equal minus a root lambda times sine of root lambda L plus b root lambda times cosine of root lambda L. Right, that's got to vanish. B times root lambda is 0, so that's not there. Right, so I've got that this thing has to be 0, or that thing has to be 0. So at this point, I said, fine. In the previous example, I didn't have the derivative, so I didn't have the square root of lambdas appearing. I just took these to say that one of the terms had to disappear. Previously, it was the cosine. Now, it looks as though it's not the cosine, it's the sine, right? This one's going to look like I need to put b is equal to 0. So I need to put b is equal to 0. I'm not going to be able to say what it is from this equation. That's just going to tell me what lambda is again. Right, so here we've gone with, this is going to complete step 2. I'll be finding lambda, getting the solutions for x here. Having done all of that, I'll go back and solve the y equation. Okay, so let's now pop up here. So what am I going to do? I'm going to say, hey, I put b is equal to 0. And this one, I don't want to put a is equal to 0 because then I get nothing. It looks as though I want to put the sine function to 0. And I'm back to the square root of lambda being an integer. There it is. Looks as though I've now accomplished what I accomplished last time. However, I should be a tiny bit more careful here because there is another way of solving this equation. And that's by putting lambda is equal to 0. If I put lambda is equal to 0, then I can apparently solve both at once. Let's give lambda as 0 a bit more of the consideration. Remember that I had x prime primed over x was equal to minus y prime primed over y. That was what I was calling minus lambda. If I put lambda is equal to 0 here, I don't necessarily get a trivial solution because it's just going to tell me that big X and big Y are linear functions. That's not trivial, right? That's some possibility. So there really are two things to keep track of. One is where I have lambda as being the square of an integer, but then also the fact that there might be a solution with lambda is equal to 0. Okay, so this is finding lambda. Let's just record what the big Y is because I haven't done that yet. Okay, so big Y, the equation for big Y is there. So it's y prime primed equals lambda y. So when I solve that, I'll have completed step 2. So this is the y equation. Right, so y prime primed is equal to lambda y. That's either 0 or n squared y. Right, if I have these two possibilities. Right, so y is then, let's do lambda is equal to 0 first. That means that it's a linear function, a constant, or something times y. So let's call it, right, so we've got an a and a b there. Right, so let's call it a0 plus b0 y. That's if lambda is equal to 0. If lambda is n squared, the auxiliary equation associated with that constant coefficient ODE, let's just write it out up here, a little bit more space. So y prime primed is equal to plus n squared y. If I search for a solution in the form of an exponential, I get the auxiliary equation. M squared is, I made a slight error there. I'll come back and fix it. Okay, when I solve this equation, I should have had lambda times L equaled n pi in order to get the sine function to vanish, because I'm no longer on the interval 0 to pi. I put it as L. So to get the sine function to vanish here, I have to get the square root of lambda times L to be an integer times pi. Okay, that means that lambda, in this case, is n squared pi squared over L squared. If L is equal to pi, I get back to where I was before. Right, I have to make sure I've got that. So here, that's not equal to n squared. It's n squared pi squared over L squared times big Y. So I forgot a factor of pi on L. Okay. Okay, so we've got the solution with lambda is equal to 0, and then the solution here is going to be an exponential. It's going to be an exponential, let's call it a e to the m y, and a b e to the minus m y, where that's m. Right? I get it straight from there. Okay. Right, I need a general solution, so I'm going to do that next. Okay, so m is n pi over L. Great, so let's looking at this. Now let's put it all back together. Let's look ahead whilst I clean up a little. So what am I getting out of this? I'm going to get things in here that are exponentials in y, or a linear function of y. And my solution for x was, it didn't have the sine function in it, right? It just had the cosine in it. So I'm going to get cosines times those things. But that's not everything, right? Because there's this possibility that lambda is 0. And when lambda was 0, if I think back to my solution for x, that's solving this with 0 there, then x is a linear function. All right, so there's that other piece. But my boundary conditions were that the derivative had to vanish at the ends. So actually, the linear function of x that I'm going to get from putting lambda is equal to 0, it's not actually a linear function, it can only be a constant. So at the end of all of this, when I'm formulating my general solution, there's going to be a bit that's got a constant in x, and then there's going to be cosines in x, plus the bits that depend upon y. But I'm going to put y is equal to 0 here to match up the boundary condition at the bottom. So that's going to involve a general solution with a constant and a bunch of cosines in it. There's my Fourier series again. But the Fourier series this time doesn't have the sine functions. That means we're going to have to think about extending functions again, but we need to extend them in a different way. And we need to use an even extension. So that's what's coming up. Right, I'm trying to put it all together. Right, so there's the lambda is equal to 0. That's part of the solution. And then I've got big X. Well, it would be a linear function, but the derivative has to vanish. So I'll just use C as a constant. That's the function of X. The Y is this thing. A0 plus B0y. Right, I've not implied any conditions in y yet. I'll be reserving that till the end. Then I've got lambda is equal to this thing, n squared pi squared over L squared. For this, I've got x was equal to, it was the A cosine. And then if that's what lambda is, I can write this as n pi x over L. And the y function is what I get from there. It's got those things in it. Maybe I should use different symbols here because I've already used an A and a B. Let's put a hat there. And a hat there. So we don't confuse the A's and the B's. So I've got an A and a B, but the B was 0. That was one of the conclusions here, right? That was in X. For the Y function, I've got this thing, A hat E to the my. That's putting m in. And then I've got a B hat E to the minus n pi y on L. Right, so there it is. That's putting it all together for the two pieces of the solution. Lambda is equal to 0, lambda not is equal to 0, putting it all together, right? So I've got all of these, there's an infinite number of those because n is any integer, and then there's this bit that comes from the lambda is equal to 0 that I add in as well. So what's my general solution? I just have to put it all together. When I formulate my general solution, I need to be as general as possible. So I want to make sure that all of the arbitrary constants can be different. Okay. So this was the step 3, right? So u of x and y equals. Right, so there's a bit that's got a constant there and a constant plus a constant times y. Right? It's x times y is the solution. And that's the lambda is equal to 0 piece. So I would have c a naught y plus c b naught y there. I have that thing. That times that. That's the first piece of the solution. And then I'm going to have my sum over n. And then I've got that times that. So I've got an a hat. And these could be different for each value of n. So let's bear that in mind by putting subscripts there. So I've got that times that. That's a cosine times the first exponential. And then, so that's times a cosine. And then I've got the an and the bn hat times e to the minus that thing. Let's avoid running into this. And here's my cosine. Great. Right, so that's taking all of these and putting them over there. All happily together as a glorious general solution. Now, we've got too many arbitrary constants. There's no point having 2 there, and 2 there, 2 there, and 2 there. We only really need 1 there, and 1 there, and 1 there, and 1 there. All right, let's change notation to emphasize that. So this one, let's call it a new constant. What should we call it? Let's call it 1/2 A0. This one here, let's call that 1/2 A0 hat. Why have I put a half in there? Well, I'm thinking about that. This one, let's call this something else. Let's call that a little an. And then there's another one here. Let's call that one a little an. They don't have to be the same though, so let's put a hat on that one. All right, so that's just changing the symbols and avoiding having paired combos of arbitrary constants. That's my general solution. Fine. Now, great. That's sort of step 3. I need to use this to make sure I can satisfy that. So that will be putting y is equal to 0 to get f, but then it's also going to involve saying that the derivative has to go to 0 as y goes off to infinity. Right, so there's 2 conditions to impose on that there. It's already looking like a Fourier cosine series. The Fourier cosine series, right, is the bit without the signs. If I have no constant and no cosine, I have a Fourier sine series. That's the Fourier series for an odd 2-pi periodic function. The Fourier cosine has no sine functions. That's a Fourier cosine series for an even function. Right, so I'm sort of getting there. There is one slightly awkward point, though, which is the period is not 2 pi. Right, I've got these cosines in here. I don't just have nx. I've got cosine of n pi on x. And so actually what I should be using is the more general Fourier series for a periodic function with any period. So let me just quickly generalize that. So if we have 2L is the period, we come along and we multiply this argument there by pi on L. I'll do it in here as well. So nx becomes nx times pi on L. And then here, instead of pi's, I get L's. Right, that's generalizing it to arbitrary period. Okay, so now we really see that we've got 1/2 A0 as the constants. We have the cosine terms. So we're almost where we need to be in terms of using this technology to figure out what the coefficients are, having made a suitable extension. Okay, before we do that, let's deal with this condition now. I've got to get a vanishing derivative when I go off to infinity. So if I differentiate this with respect to y, it gets rid of that term, and I get this thing. And then I get derivatives of those two. But then I have to make y go off to infinity and get nothing at the end of the day. I've got a whole bunch of growing exponentials. Right? Those explode as y goes off to infinity. So the only way of making sure this goes to 0 is I first of all get rid of those. I really need to get rid of these because they will explode as y goes off to infinity. So those have to all go to 0 for uy to 0 as y to infinity. In fact, once I've got rid of those, these all decay exponentially, so they're perfectly fine. The constant disappears because I have to do a derivative in y. So this is good. These are good. This one, when I do the derivative in y, I've got to get 0. But the derivative in y leaves that constant. So that one's also got to go to 0 if I'm going to have a 0 derivative as y goes off to infinity. So, actually, this condition gets rid of half the terms. I have that u is 1/2 A0 plus the sum from n is 1 to infinity of an e to the minus n pi y on L cosine of n pi x on L. Right, now we'll finally put the complicated condition on there. F of x has got to be 1/2 A0 plus an cosine n pi x on L, summed on n. Okay, now we really see that we've got a Fourier cosine series, so what we must be dealing with is an even function, and the period is 2L, it's not 2 pi anymore. Great. Well, what's the last step in the argument. Let's get rid of the pinky bit in the middle here. And then we can complete the argument. We have to make the extension in order to see how we can do this and find a formula for the coefficients. And that's the last bit. Looks like I'm vaping here. I'm home. Okay. Right. Great. Let's do it. So, f and u are defined for that interval. We'll extend to minus L to L as even functions. And then as 2L periodic functions. Oops. Right, I'll make it fully periodic. So this is the 2L periodic even extension. I'm playing that game where I have something defined there, I then go there, making it even, then I make it periodic and get the whole line. Right? That means I can represent f and u as Fourier cosine series. A bit more space is needed. And the important thing is that I get a formula for A0 and AN. There's the general formula over there, but I don't have the B, and A0 and AN I can get from just integrating from 0 to L, multiplying by 2 over L, taking f of x, and multiplying by either 1 or cosine of n pi x over L dx. That's the key formula that tells me how to do it, given f. All right, so we've solved the PDE, all right, we've fully dealt with everything at this point. We've got my solution. Right, this is the u of x and y. This is what it's got to match up with along that section of the domain. And I get the coefficients from doing that integral. So in a practical problem, the only other algebraic exercise that one might be charged with doing would be to calculating those things for a given f. The Fourier series coefficient calculation. But at that point, we've solved the problem and we're done. Right? Now, I've done it for two specific examples. Let me just make some general comments now, and then we'll conclude. So the first example that we did was the heat equation. The second one was Laplace's equation. The first problem ended up with a bunch of sine functions. We had a Fourier sine series. That meant that we needed to do some particular extension outside the original domain of the PDE. It was the odd 2 pi periodic extension. For the Laplace problem, this one down here, we ended up with constant and cosines, Fourier cosine series, and we needed to make an even extension. Those differences are not because of the PDE, they're because of the boundary condition. Let me just emphasize that. With a nice clean board. Okay. So what was the feature that in particular gave us the sine series or the cosine series? Let's first address that. So when the smoke clears, literally, okay, well, in the first problem, we had u of 0 and t is equal to u of pi and t is 0. Right, I needed to get the thing to vanish at those particular points. The sine functions do that. And we're going from 0 to pi. Right? Sine of nx, if I put pi in there, guarantees those boundary conditions. Right? And that means we end up with a bn times a sine nx type series. Right? And to relate it to the Fourier series stuff, we then just did the odd extension and made it 2 pi periodic. Right, so we've gone from 0 to pi, we make the extension to minus pi to pi, and then we end up with a 2 pi periodic function. Right, so it was those boundary conditions that led us to that. That was problem 1. Problem 2, we actually had derivative conditions. And we had the other one at L, not pi. Right, so we were dealing with that. So these conditions are guaranteed by the cosine. And in fact, the argument of the cosine is now slightly different because I'm going from 0 to L now. Right, we needed that kind of a cosine. Gives us the right function to satisfy the boundary conditions. But also, a constant worked. Right? That was the lambda is n squared pi squared over L squared case. And this is lambda is equal to 0. Right? So you needed both of those to get it right. This is the constant in the Fourier cosine series, and that's the rest of the series. Right? We then extended to minus L to L, right, instead of minus pi to pi, and then we made it periodic, but it was 2L periodic. Right? So when I look at the boundary conditions, right, there and there, if it's the u function of the solution itself must vanish, then I end up with a Fourier sine series, and the period is twice that. If I've got derivative conditions, I end up with the cosine and the constants, and the period is twice that. That's where that came from. It's not the PDE, it was the boundary conditions. Now, let's just think about one other feature, which is the split of the initial conditions and boundary conditions, right? In general, in all of these problems, there's a split that has to be made, right? There's the simple ones, and there's the complicated leftovers. Right, you do these first, and you do those last. Right, this is where the f of x usually appears. Right, and these ones, they tell you lambda, the separation constant. Right, that's generally how it works. Okay, now, in order for this to be true, you need homogeneous conditions. i.e., you need u to be 0 or ux to be 0. If that's what you have, then you can use these conditions first and they will tell you lambda. If you have something on the right there, something else, it doesn't work. That means that the boundary conditions are inhomogeneous. And when the boundary conditions are inhomogeneous, or even the PDE has got some inhomogeneous terms in there, you have to do something different. You need a revision of separation of variables if PDE, or the boundary conditions, are inhomogeneous. And that's an important point. Okay, that's actually the last couple of lectures of the course, and there's already a video posted on the website for that. Okay, so you have to do something slightly different. There's an initial preparation step before step 1, as I called it. There's a step 0 that you have to go through here. Otherwise, right, you've got these simple homogeneous looking conditions that simplify the solutions of the ODEs and tell you what lambda are. And in this case, you need a general solution with the whole bunch of constants in there. And in 256, that's where a Fourier series will come in. And you have to make that little argument about extension in order to come up with the formula that tells you the coefficients, which is not there anymore. Okay, so that's where the sines or the cosines came from. Right, this is underneath the methodology. There's one last thing. I don't know whether you got bothered by this, but it's something that we need to discuss. So I'm going to bring it out into the open. It's about the separation constant, and it's about the sign of it. Okay, so let's pause a second. I'll just give myself a clean sheet here. What am I talking about? When I wrote down the ODEs, it came from demanding that I had a function of x is equal to a function of t or a function of y, and then saying that they had to be equal to the separation constant. And in both cases, I chose minus lambda. Why did I choose minus lambda? If you put the wrong sign, you end up having to do twice the amount of effort. So it's really useful to put the right sign in. Let me indicate why I say that and how you can see it all. So this is all about the sign of the separation constant. Right, so we had x prime primed over x is t prime primed over t in the first case. In the second case, I had that. Right? And what we did in both cases, we said that that was minus lambda. But why the minus? Okay, first of all, let's do the math reason. Let's imagine that we made the opposite choice. Let's have a look. So the x problem, you would get x prime primed. Instead of getting what we had before, which was a plus lambda x, we'd get a minus sign. We would have switched the sign there. That's what we would have got. Actually, that would mean that the solutions for x would be e to the plus or minus the square root of lambda x. Nothing wrong with those as solutions, right? Just get exponentials. We got sines and cosines, but these would, with this choice, be exponentials. But we have x of 0 is x of pi is equal to 0. That was in the first case. Or we had x primed of 0 is x primed of L is 0. We had these 2-point boundary conditions which said that I had to get 0 at both for either the function or it's a derivative. Now if you use exponentials and you try to get those exponentials to satisfy those conditions, you're ultimately going to find out that your solutions have to be trivial. The exponential, one grows, one decays. I can't get them to magically cancel out at 2 different points. And I can't get the derivatives to cancel out at 2 different points. Right, so it fails the test of the boundary conditions. So if you put plus lambda rather than minus lambda, you end up with exponentials and you can't satisfy the boundary conditions. But you have to be able to satisfy the boundary conditions. You have to be able to solve the problem this way. And so you say, oh, well, okay. The only way to do it is to make lambda negative. That puts an imaginary constant there, turns the exponentials back into sines and cosines. And sines and cosines can effortlessly satisfy those 2 0 conditions. We need functions here that have multiple zeros. Sines and cosines have that. Exponentials don't. That's the mathematical reason. Right, so if you'd have been coming at this problem and made the wrong choice, you would have deduced that you can't solve the problem and suddenly realized, oh, damn, I should have had the opposite sign to lambda. So it would have corrected itself, but you would have done twice the amount of work. That's the mathematical reason. Okay, what's another reason? Well, another reason is sort of connected to the physics of the problem. Now, that doesn't always provide you a useful piece of insight because maybe you don't know what the physics of the problem is. At least for the heat equation, that's this problem, you do know something about what diffusion does. Diffusion likes to wipe things out. It likes to smooth stuff out. Structure gets diffused. Things get smoother with time. That's the smoothing action of diffusion for you. Gets rid of stuff. Okay, well, let's now think about this part of the problem, right? Not that one. Let's say we've got the time equation. Right, so this is the physics reason. So t primed over t is equal to, well, we put minus lambda. We ended up with t proportional to e to the minus lambda t. That's exponential decay. If you start with something, it diffuses away. That's physically sensible. If you'd have switched the sign, I would have ended up with something that grew with time. Things just keep growing. That's not what diffusion is going to do. So this is plausible for diffusion. This is implausible. This is obviously more workable than this because you need a bit more insight there. But there's usually multiple reasons of choosing the right sign. Okay, once you've done it a few times, you realize what sign you should choose in order to save yourself work. And it's really because one of the equations that you get from here, you have to solve it and put 0 in 2 places. And only sines and cosines are good for that, not the exponentials. That's really the crystal clear rationale for choosing the sign of the separation constant. Now, I guess I've got 1 more minute. Let me just illustrate that with the wave equation. I haven't talked about the wave equation yet, so let me just illustrate the wave equation. So here we go. The wave equation. That's UTT is UXX, once I've scaled the coefficients away. Right, so that's what we're dealing with. Step 1 in the methodology of separation of variables would be to put big X of X and big T of T. I plug those in there, what would I get? You've probably already figured it out because it's very similar to what we did in the other 2 examples. We end up with T prime primed from there, X prime prime from there. This one had an X with it, that one had a T with it, so we divide by those. And I get that. Right, that's from separating variables, plugging that into there, and dividing by big X and big T. That's usually what you do in all of these problems. So that's the function of T. That's your function of X. Now, what problem would you be typically solving with the wave equation? Well, we'd be given this, but then we'd be given those other conditions. And let's imagine that we've got a stretched string, a guitar string, and U is the deflection. All right, so this is U of X and T. That's what we're searching for. So we would be providing 2 initial conditions because there are 2 time derivatives. So for example, we could be saying that U at T is equal to 0 is some given F, or we could be saying that du dt at T is equal to 0 is some other function. That's like pulling it and giving it some initial displacement. That's what the F is physically representing. And the G would be if I came along and I hit it and gave it an instantaneous velocity. Right, so that would be plucking, and that would be plucking and banging. Anyway, so those are the initial conditions. They're clearly complicated. Right, I've got some general functions in there. So those you save to last, right? And you deal with them using a general solution. Right, on top of this, I'm going to need to say something else. So for the stretched string, you would just simply say that the deflection is 0 at the ends because I'm holding them. So you would say that U of 0 and U of L, if that's the length, is 0. Right, those would be the boundary conditions. Right, these are the initial conditions. You save those to last. You deal with these immediately once you're solving those equations, and you want to put in a separation constant there in order to be able to solve those, right? That's in X, right? So it's this bit of the problem that you want to be able to solve, and you need to get the function to vanish at 2 particular points. You need sines and cosines, so put the minus sign in there. Right, so that's the mathematical reason for the choice. What's the physical reason? Well, when I solve the T problem here, right? It's the same ODE, right? T prime prime plus lambda t is equal to 0, and x prime prime plus lambda x is equal to 0. All right? So sines and cosines for x, I get sines and cosines for t. Things oscillate in time and space. Right, well, when you excite a guitar string, it oscillates. Physically, that's exactly what you want to do. You want to get the guitar string to vibrate and oscillate in time, and the choice of minus lambda here gives you solutions in time that oscillate. So that's physically sensible for the wave equation. If I'd have got the wrong sign in there, I would have had exponentials in space that couldn't satisfy the boundary conditions, and then I would have got exponentials in time, which wouldn't oscillate, wouldn't be a guitar string ringing. Right? So it would be physically implausible. Right, so that's the analog of the mathematical and the physical reasons for the wave equation. And at this point, we're now set up to solve all of the problems in the world by separation of variables. And I finish.